I want to convince you that there's another equation besides the definition of capacitance that says it's equal to a ratio of charge stored in comparison to voltage applied. The other equation, for at least for a parallel plate capacitor, says capacitance is equal to permittivity of free space multiplied by the area of the parallel plates divided by the distance between them. So let's say that the parallel plates that form a PPC in this example have a surface area of A and are separated by a distance D. Here's another example where the plates, instead of being rectangular, so clearly the area in our first example would be length times width. Here area would be pi r squared. But still, whether the plates are rectangular or circular, the capacitance is the permittivity of free space, 8.85 times 10 to the negative 12th. What are the units for this? Coulomb squared per Newton meter squared, right? Yep. Multiply that permittivity times the ratio of the area over the distance, and you've got the capacitance. Well, where does this equation come from? Well, we can actually derive it from this equation. So this is the more fundamental equation. This is true for all capacitors. This equation is only true for the parallel plate capacitor. So let's see how we can derive the one equation from the other. So again, we've got a parallel plate capacitor with a spacing of D. And let's say, for example, the top plate is positively charged and the bottom plate is negatively charged. And both plates have the same surface area, A. Don't forget there's an electric field. It's rather uniform in the spacing between the plates. I say rather uniform because as we get toward the edges, there's some bending and curving of the electric field. But as long as we stick to areas close to the interior, then the electric field is uniform. Now, how do we determine the value of that electric field? This would be a good case for Gauss's law, right? So we might imagine maybe a cylindrical Gaussian surface like this. And it intersects the top plate. So there's some amount of positive charge inside of this Gaussian surface, represented by this dark red shaded area. So there's our Qin. Gauss's law tells us that the total electric flux, calculated as this surface integral, is equal to the amount of charge inside the Gaussian surface divided by epsilon naught. The electric field is uniform, and the electric field does not pass through the side walls of our Gaussian surface, so there's no flux through the sides. There's only flux through these end caps. And keep in mind the electric field also goes out in this direction as well, right? Becomes more non-uniform toward the edges on the outside than the inside. But in any case, as long as we draw the area of our Gaussian surface, or at least the area of the end caps, right? We maybe call this A prime versus A. So A prime is the area of the end cap of the Gaussian surface, and as long as A prime is much, much less than A, then the electric field will be uniform through these end caps, and that's the region where we have flux. So because it's uniform, we get rid of the dot product, we take the e out of the integral sign, and we just get E times the total surface area through which there is flux is equal to Q in over epsilon naught. Now let's say that sigma represents the charge density in units of coulombs per square meter. Then the amount of charge inside would be equal to sigma multiplied by A prime. So let's make that substitution. Now the total area through which there's flux is the top and the bottom end caps of my Gaussian surface, and so we get E times 2A prime is equal to sigma A prime over epsilon naught. So you see we can cancel out the A prime, and we get to the result. And this is all review from our previous lesson. Anyway, the electric field just due to the top plate, not the total electric field, but the electric field just due to the top plate, then would be equal to sigma divided by 2 epsilon naught. And we can make a substitution. Sigma is equal to that positive charge on this upper plate divided by A. Not A prime, but A. So we substitute, and we get E is equal to Q over 2 epsilon naught A. Now that's just the electric field due to the upper plate. If we took the bottom plate and made a second Gaussian surface that intersects this negative charge, all that's going to happen is, by superposition principle, it doubles the effect. So the net electric field is equal to 2 times Q over 2 epsilon naught A. Or in other words, the net electric field in the space between the parallel plates of a parallel plate capacitor is equal to Q over epsilon naught times A. Where are we going with this? Well, remember now, we're trying to derive this very specific equation for parallel plate capacitors from this very fundamental or general equation that describes all capacitors. And we've got an expression for electric field, and our fundamental equation for capacitance involves electric potential difference, and you know there's a relationship between those quantities, right? Electric potential difference is a line integral based on electric field. Electric potential difference is equal to negative E dot ds. So again, we've got our parallel plates. And the uniform electric field between them. So let's just take a line integral that goes from, how about, we always go from point A to point B, right? So let's go from the bottom, from our negative plate, to the top, our positive plate. Then the potential difference between the two plates is equal to negative the integral of E dot ds. And let's just make a reference where our displacement is going along this y-axis. And we'll say y equals 0 at the bottom plate. If the plates are separated by a distance d, then y equals d at the top plate. So we can make two substitutions here. E is replaced with Q over epsilon naught times A, and ds is replaced with dy, and we're going to integrate as we go from 0 to d. So our change in voltage is, all of these are constants, so the integral of dy from 0 to d just gives us d. So the change in voltage is q d over epsilon A. And then we can present once again the most fundamental, most general equation that describes capacitors that says capacitance is equal to the charge stored on the positive plate in comparison to the potential difference between the two plates. So this is equal to Q divided by QD over epsilon A. And now the Q cancels out, and we get capacitance is equal to epsilon naught A over D, which is exactly what we were trying to prove. So that worked out nicely.